Distance is a word you learned as a child. You understand it instinctively. The distance from your bed to the bathroom, the distance to school, to work, to the grocery store. You've walked distances, you've driven them, you've flown across them on airplanes, watching the ground shrink beneath you, counting hours until arrival. You know what distance means, but you don't. Not really. Because the distances you know, the ones you've experienced, the ones that feel real to you, they exist in a tiny bubble of human experience. They're the distances that bodies can cross, that minds can imagine, that make sense within the frame of a human lifetime. They're comfortable, manageable, comprehensible. The universe does not operate at this scale. When you step outside that bubble, when you try to understand the actual distances that separate objects in space, something happens to your intuition. It doesn't just struggle, it fails completely. The numbers become meaningless, the comparisons break down. Your mind reaches for familiar anchors and finds nothing to hold on to. This isn't because you lack intelligence or imagination. It's because distance, real cosmic distance, operates so far beyond human scale that understanding it requires abandoning almost everything your experience has taught you about how space works. What follows is not a collection of impressive numbers. It's an attempt to walk you through what distance actually means when you leave Earth behind. We'll start where you are, with the distances you know, and we'll expand outwards slowly, carefully, until we reach the point where distance itself becomes something strange and unfamiliar, where it stops being a gap to cross and becomes something else entirely, a measure of time, of history, of what's possible and what will forever remain beyond reach. By the end, the word distance will mean something different to you than it does right now. Let's begin with the simplest version of distance you know, the kind you can cross with your own body using nothing but time and effort. You know how far you can walk. You've walked to destinations your entire life, and somewhere deep in your body, below conscious thought, you understand what a mile feels like, what 5 miles costs in effort and time, what 10 miles means for your day. This is the fundamental human unit of distance, not feet or meters, but the lived experience of moving your body through space until you arrive somewhere else. A mile takes roughly 20 minutes to walk at a comfortable pace. You can feel that duration. You know what 20 minutes feels like in your legs, in your breathing, in the slow passage of scenery around you. 5 miles becomes an hour and 40 minutes, long enough to listen to a podcast, long enough to watch the sun move across the sky, long enough to feel the achievement of arrival. 10 miles approaches 3 hours, the outer edge of what feels reasonable for a casual walk, the point where you start to think about water, about rest, about whether this journey is worth making on foot. This is your scale, the human scale. Everything about your intuition for distance is calibrated to these numbers, these experiences, these physical limits. Your ancestors walked everywhere. For most of human history, the distance you could walk in a day determined the size of your world. 20 miles was an enormous journey. 40 miles might take 2 full days. 100 miles could mean a week of travel, carefully planned with rest stops and supplies. The world was small because walking made it small. Even today, in a world of cars and planes, walking remains your baseline. When you see a destination on a map, some part of your brain, without asking permission, calculates how long it would take to walk there. 2 miles away, half an hour, 10 miles, you'd need most of a morning. This calculation happens automatically, invisibly, because walking is the most fundamental relationship your body has with distance. Now, extend that understanding. Imagine you wanted to walk across your country, wherever you are. If you're in the United States, walking coast to coast means covering roughly 3,000 miles. At 20 miles per day, a pace that would exhaust most people, that's 150 days of continuous walking. 5 months. No rest days, no breaks. Just walking, every day, sunrise to sunset, until the ocean appears on the opposite side of the continent. Most people who actually attempt this journey take closer to 6 or 7 months, because bodies need recovery, because weather interrupts, because walking 20 miles every single day without exception is harder than it sounds. Your feet develop blisters that make each step painful. Your joints ache from the repetitive impact. Mental fatigue sets in after weeks of identical days. The romantic notion of a cross-country walk collides with the physical reality of what it means to cover 3,000 miles on foot. But it's still imaginable. People have done it. You could conceive of doing it yourself even if you never would. The distance is vast by human standards, but it remains human. It fits within a single lifespan, within a single sustained effort, within the realm of possible experience. You can picture the journey. You can imagine the monotony, the small towns passing by, the changing landscapes, the gradual accumulation of miles. It would transform you, certainly, but it wouldn't break you. It's the kind of distance a human being can comprehend because it's the kind of distance a human being can actually cross. Now consider walking around the Earth's equator, 25,000 miles. At 20 miles per day, that's 1,250 days, 3 years and 5 months of continuous walking, except you can't walk continuously around the Earth because oceans exist, because terrain becomes impassable, because the simple geometry of a sphere doesn't translate into walkable paths. But set those practical concerns aside and consider just the time. 3 years of walking, every day, to return to where you started. You can still imagine this, barely. 3 years is a comprehensible duration. Long, yes. Difficult, certainly. But people spend 3 years in college, 3 years deployed overseas, 3 years working toward a specific goal. The human mind can wrap itself around 3 years. It's a large portion of a life, but it's not beyond understanding. You can picture what you were doing 3 years ago. You can imagine what 3 years from now might look like. The span feels real. This is important to establish because this is where your intuition still functions. These are distances that, while extreme, remain tethered to human experience. You could walk them, theoretically. It would cost you time, enormous amounts of time, but the time itself is measurable in familiar units, months, years, portions of a single human lifetime. The distance feels vast, but it's a vastness that maps onto something you understand: duration, persistence. The slow accumulation of days into larger blocks of time. Hold on to this feeling. This sense that distance, even great distance, is ultimately just a matter of time and persistence. That if you kept moving, kept putting one foot in front of the other, you would eventually arrive. This is what distance means to a human being. A gap that time and effort can close. A space that separates one location from another, but a space that can be traversed, crossed, conquered, through this simple application of continuous movement. Now let's introduce speed. Because walking, as natural as it feels, is not the fastest way a human body can cross distance. Running covers ground faster, perhaps 3 times faster than walking for short bursts, but no one can run for 3 years straight. No one can even run for 3 days straight. Running is a sprint, not a solution to distance. It trades endurance for velocity and loses the trade quickly. Bicycles represent a better compromise. They let you sustain higher speeds for longer periods without destroying your body. 20 miles on a bicycle might take an hour and a half instead of 5 hours walking. The same distance compressed into a fraction of the time. Your muscles still do the work, but the machine multiplies your effort, translates it into greater speed, covers more ground with each rotation of the pedals, but bicycles still keep you connected to the distance. You feel the hills, you feel the wind, you feel the hours accumulating in your legs and back. The distance doesn't disappear, it just becomes more manageable. You're still earning each mile with effort, still paying for the journey with your body's energy. Cars change everything. At highway speeds 70 miles per hour, you could cross the United States in roughly 43 hours of driving. Not 43 days. 43 hours. 2 days if you barely stopped. The same continent that would take 5 months to walk collapses into a long weekend road trip. Distance compresses under speed. What felt vast becomes manageable. What required months of dedication becomes a brief inconvenience, a test of patience rather than endurance. But notice what's happening. You're not experiencing distance anymore. You're experiencing time while distance passes around you. You sit still in a cushioned seat. The landscape moves past your windows like scenery in a film. Hours accumulate on the clock, but your body never feels the 3,000 miles. You never earn the distance with effort. You never pay for it with exhaustion. Speed has created a buffer between you and space itself, a barrier that separates your body from the physical reality of the gap you're crossing. This is the first separation, the first moment where distance stops being something you cross with your body and becomes something you defeat with technology. You're still on Earth. The distances are still planetary, still comprehensible. But you've already begun to leave behind the intuitive understanding that comes from walking, from feeling each mile accumulate in your muscles and lungs, from knowing in your bones what distance costs. And we've only just started. Because cars, fast as they seem on a highway, are still extraordinarily slow by the standards of distance we're about to encounter. A car moving at 70 miles per hour feels fast, because human bodies evolved to move at 3 miles per hour. The comparison makes cars feel like miracles of speed, but compared to what's coming, compared to the speeds that become necessary when you try to cross real cosmic distance, a car is barely moving at all. It's still operating on a human scale, still measuring speed in terms that make sense relative to walking. Let's go faster. Airplanes dissolve distance in ways that cars cannot approach. A commercial jet cruises at roughly 550 miles per hour, nearly 8 times faster than highway driving. At this speed, crossing the United States takes 5 hours instead of 2 days. The continent that required 5 months of walking, that demanded 43 hours of driving, becomes a single afternoon in the air. You board in New York before lunch. You land in Los Angeles in time for dinner, local time. The sun barely moves in the sky relative to your position beneath it. But something strange happens at airplane speeds. Distance stops feeling like distance at all. When you drive, you watch the landscape change gradually. Cities give way to farmland. Farmland becomes desert. Desert transforms into mountains. You see the transitions, you feel the progression. But in an airplane, you see only departure and arrival with nothing meaningful in between. The ground becomes abstract, a map beneath you, details erased by altitude. The 3,000 miles might as well be 300. You have no sense of crossing them. You simply wait and then you're elsewhere. This is what speed does. It doesn't just reduce travel time, it fundamentally alters your relationship with the space you're crossing. The distance becomes something that happens to you rather than something you traverse. You become a passenger in your own journey, watching time pass while distance collapses around you, until the gap between locations feels more like an inconvenience than a physical reality. Now consider the fastest speed you've ever personally experienced. For most people, this is an airplane, 550 miles per hour. It feels impossibly fast. You're moving faster than sound travels through water, faster than the fastest animal on Earth by a factor of 5. At this speed, you could circle the equator in roughly 45 hours. The walk that would take 3.5 years becomes less than 2 days. Speed has compressed the planet into something you could traverse in a weekend if you didn't need to stop for fuel. But 550 miles per hour is extraordinarily slow by the standards we're approaching. It's slow compared to the speeds humans have actually achieved. It's slow compared to what becomes necessary when you try to leave Earth's surface and venture into the space beyond. The space shuttle, during its operational years, orbited Earth at 17,500 miles per hour. Not 500, 17,000. This number is difficult to comprehend because you've never experienced anything close to this speed. 17,000 miles per hour means crossing the United States in 10 minutes, coast to coast in less time than it takes to drink a cup of coffee. The distance that took 5 months to walk, 2 days to drive, 5 hours to fly, collapses into 10 minutes. Distance at this scale stops meaning what it meant before. It stops being a challenge and becomes almost trivial. Earth shrinks beneath speeds like this. The planet becomes small. At orbital velocity, you circle the entire Earth every 90 minutes. Every hour and a half, you return to where you started. 16 times per day, you watch the sun rise and set. The 25,000-mile circumference that would consume 3 years of walking becomes an hour and a half of waiting. The enormity of the planet, the sense of Earth as this vast world containing continents and oceans and billions of people, dissolves into something you can lap in the time it takes to watch a movie. This is the speed necessary to stay in orbit, to balance gravity's pull with forward motion, to prevent falling back to the surface. 17,000 miles per hour isn't a choice, it's a requirement. Go slower and you fall, go faster and you escape. This exact speed, this precise velocity, keeps you circling endlessly at the edge of space. But even this speed, even 17,000 miles per hour, becomes insufficient the moment you try to go anywhere beyond Earth orbit. Reaching the moon requires accelerating to 25,000 miles per hour. This is escape velocity, the speed needed to break free from Earth's gravitational grip entirely, to stop circling and start travelling outward into the solar system. At 25,000 miles per hour, the journey to the moon takes 3 days, not 3 years. Not 3 months, 3 days. 240,000 miles crossed in 72 hours. The Apollo astronauts experienced this. They left Earth on a pillar of fire, accelerated to speeds no human had ever reached before, and then coasted through empty space toward a distant grey sphere. For 3 days they travelled, watching Earth shrink behind them, watching the moon grow larger ahead, crossing a gulf of space that walking could never bridge, that driving couldn't approach, that even airplanes would find insurmountable. And yet, even at 25,000 miles per hour, even at speeds that let you escape Earth entirely, the journey still took 3 days. Not 3 hours, not 3 minutes. 3 full days of travel to reach our closest celestial neighbour, the object that appears largest in our night sky after the sun. The destination that seems near because we can see it clearly with our naked eyes. This should tell you something. The moon feels close. It looks close. You can see details on its surface without a telescope, can watch it move across the sky, can feel its presence as a companion to Earth. And reaching it, travelling the distance that separates us from it, requires 3 days at 25,000 miles per hour. 3 days at a speed 60 times faster than a jet airplane. 3 days at a speed that would let you circle Earth's equator in 1 hour. 3 days to reach something that seems near. Let's put this in perspective by returning to slower speeds for a moment. If you tried to drive to the moon at highway speeds 70 miles per hour, the journey would take 143 days. Nearly 5 months of continuous driving through empty space. If you walked at 3 miles per hour, it would take 9 years. 9 years of walking without stopping, without sleeping, without rest, to cross the gap between Earth and the moon, the same gap that Apollo 11 crossed in 3 days. Speed matters. It doesn't just reduce travel time, it determines what's possible. At walking speed, the moon is unreachable within a human lifetime. At driving speed, it's theoretically possible but absurd. At airplane speed, 500 miles per hour, the journey takes 18 days. Still possible, but impractical. Only at 25,000 miles per hour does the journey become something humans can actually attempt and survive. This is the first real lesson about cosmic distance. Human speeds, the speeds your body can produce, the speeds that feel fast in daily life, are useless beyond Earth. Completely, utterly useless. Walking speed is irrelevant. Driving speed is irrelevant. Even airplane speed, which feels miraculous, which seems to erase distance within our atmosphere, becomes pathetically slow the moment you venture into space. The distances out there, even the nearby distances, even the gaps between objects in our own solar system, require speeds that human evolution never prepared us to understand. Speeds that don't feel fast because you've never experienced them. Speeds that can only be described with numbers that sound abstract and unreal. 17,000 miles per hour. 25,000 miles per hour. Numbers so large they lose meaning. They become noise. They stop connecting to anything in your lived experience. And we've only talked about the moon, the closest object to Earth other than artificial satellites. The near neighbour, the easy destination. We haven't discussed planets yet. We haven't mentioned the sun, or the edge of the solar system, or the distances between stars. We're still in Earth's immediate neighbourhood, still discussing distances that spacecraft have actually crossed, that humans have actually travelled, and already speed has become something alien. Already the numbers have started to exceed intuition. Already the gaps feel larger than they should. Let's keep going. Let's see what happens when we try to go farther. When we point our spacecraft toward the planets and attempt to cross the real distances within our solar system, the spaces that separate worlds, the gulfs that make the moon look close by comparison. This is where distance starts to break. Mars appears in the night sky as a reddish point of light. You can see it without a telescope, without any equipment at all, just by looking up on a clear evening. It's visible, present. Close enough to observe with your naked eye, close enough to feel like a neighbour in the cosmic sense. When people talk about colonising another planet, they talk about Mars. When science fiction imagines humanity's first steps beyond Earth, it imagines Mars. The planet feels near because we can see it, because we've sent machines there, because it exists in our cultural imagination as the next destination. The distance to Mars varies because both Earth and Mars orbit the Sun, and their paths bring them closer together and farther apart in a continuous cycle. At the closest approach, when the two planets align favourably, Mars sits roughly 35 million miles from Earth. At the farthest separation, when they're on opposite sides of the Sun, the gap grows to 250 million miles. But let's focus on the near distance, the best case scenario, the moment when Mars is as close as it ever gets, 35 million miles. If you tried to drive to Mars at highway speed 70 miles per hour, the journey would take 57 years. Not 57 days. 57 years of continuous driving without stopping, without slowing, without deviating from a perfectly straight path through empty space. You would grow old in the driver's seat. You would spend your entire adult life travelling toward a red dot on the horizon that grows infinitesimally larger with each passing year. Most people would die before arriving. The distance would outlast them. If you walked, the journey would take 1,300 years. Longer than the United States has existed as a country, longer than the entire medieval period of European history. You would begin walking before the Renaissance, before the printing press, before gunpowder reached Europe, and your distant descendants, generations removed, might eventually arrive at a planet you never lived to see. These numbers should sound absurd because they are absurd. No one would drive to Mars. No one would walk. The entire thought experiment is ridiculous. But it's ridiculous precisely because it exposes how vast 35 million miles actually is. When you use human speeds that feel normal and comprehensible, the distance becomes impossible. It exceeds human lifespan. It exceeds human civilization. It becomes a gulf so wide that crossing it with familiar velocity is not difficult but literally impossible. So we use faster speeds, the same speeds that took us to the moon. The spacecraft that have travelled to Mars accelerate to roughly 25,000 miles per hour, sometimes faster depending on the mission profile and the alignment of the planets. At this speed, at the velocity necessary to escape Earth's gravity, the journey to Mars takes approximately 7 months when conditions are optimal. 7 months of travel through empty space to cover 35 million miles. 7 months feels manageable. Astronauts have spent longer than that on the International Space Station. Submarines stay submerged for similar durations. 7 months is a long time, certainly, but it fits within human tolerance. It's not pleasant, but it's survivable. We can imagine enduring it. But notice what just happened. We jumped from 57 years at highway speed to 7 months at spacecraft speed. The distance didn't change. 35 million miles remained 35 million miles. But by increasing velocity, by moving nearly 400 times faster than a car on a highway, we compressed the journey from multiple human lifetimes into a duration that one human could survive. This is the brutal mathematics of space travel. Distance doesn't care about human lifespan. It doesn't accommodate our biological limitations. It simply exists, vast and indifferent. The only variable we can control is speed. Go fast enough, and you might live long enough to arrive. Go too slow, and the distance kills you through time, through the simple fact that you age faster than you travel. And Mars is close. Mars is our neighbour. Mars is the easy destination, the one we've actually reached with robots, the one we seriously discuss visiting with humans. If Mars at 35 million miles requires 7 months of travel at 25,000 miles per hour, what happens when we look farther? What happens when we try to reach the outer planets, the giants of our solar system, the worlds that orbit far beyond Mars? Jupiter sits roughly 465 million miles from Earth at its closest approach. This is more than 13 times farther than Mars. At 25,000 miles per hour, the journey takes nearly 2 years. Not 2 months, 2 years. 730 days of travel through darkness to reach a planet we can see with our eyes. A planet that ancient humans observed and tracked. A planet that feels like it should be reachable because we've known about it for thousands of years. 2 years in a spacecraft, 2 years of eating packaged food, breathing recycled air, living in a metal container no larger than a small apartment, watching Earth shrink to a point of light behind you, watching Jupiter grow slowly, painfully slowly in the window ahead. 2 years of waiting to cross 465 million miles of nothing. Saturn is farther. At its closest, roughly 800 million miles separate Saturn from Earth. The journey at spacecraft speeds takes 3 years and 3 months. Not the abstract 3 years it would take to walk around Earth's equator, but 3 actual years of continuous space travel. 3 years of isolation, 3 years of risk, 3 years of distance accumulating so slowly that the human mind struggles to maintain perspective on the journey. You would leave Earth, and by the time you arrived at Saturn, everyone you knew would have aged, moved on, changed. The world you left would not be the world waiting for your messages, arriving at light speed after additional minutes or hours of delay. Uranus sits 1.7 billion miles away at closest approach. The journey takes 6 years. Neptune, at 2.7 billion miles, requires 9 years of travel. 9 years to reach a planet in our own solar system. 9 years moving at 25,000 miles per hour, a speed so fast that you could circle Earth in 1 hour, and yet still requiring nearly a decade to traverse the distance between Earth and the outermost planet orbiting our Sun. This is where your intuition for distance begins to fail completely. Because these aren't interstellar distances, these aren't the gaps between stars, these are distances within our solar neighbourhood, within the family of planets that orbit the same star we do, within what should be our local environment. And yet they're so vast that crossing them consumes years of human life, even at speeds that seem impossibly fast by everyday standards. The Voyager 1 spacecraft launched in 1977, accelerated to roughly 38,000 miles per hour, and has been travelling outward ever since. For more than 47 years it has moved through space without stopping, covering distance that walking could never approach, that driving couldn't imagine, that even our fastest spacecraft can barely manage. In those 47 years, Voyager 1 has travelled roughly 15 billion miles. It has left the solar system behind, crossed into interstellar space, ventured farther from Earth than any human-made object in history. 15 billion miles in 47 years. And yet Voyager 1 hasn't reached anything. It's not approaching another star. It's not nearing another planet. It's simply moving through empty space, through the vast gulf that separates our Sun from other suns, travelling at a speed we consider phenomenal and covering distances we consider enormous. And in all that time, in all those miles, it has barely begun to cross the real distances that exist in the galaxy. The space between stars is so much larger than the space between planets that Voyager 1, moving for half a century, has barely made a dent in the journey. To reach the nearest star system to our Sun, Alpha Centauri, Voyager 1 would need to travel for 73,000 years. Not 73 years, 73,000 years. Longer than human civilization has existed, longer than agriculture, longer than writing, longer than cities. Voyager 1 could travel from now until the end of recorded human history and back again, multiple times, and still not arrive at the closest star to our own. This is what distance means beyond Earth. This is what happens when you try to use human speeds, or even enhanced human speeds, to cross cosmic space. The numbers stop making sense. The durations exceed comprehension. The gaps between objects become so large that speed, even extreme speed, even the fastest velocity we can produce, becomes insufficient. Not slow, insufficient. Unable to bridge the gulf within a time frame that matters. And we still haven't discussed light. We still haven't introduced the fastest speed that exists in the universe, the speed that physics itself uses to measure cosmic distance. Because even light, even the ultimate speed limit of reality, struggles with the distances we're approaching. Even light takes time to cross the space between stars, between galaxies, between the structures that populate the universe. Let's talk about light. Let's talk about the one speed that actually works for cosmic distance, and why even that speed reveals how vast the universe truly is. Light moves at exactly 186,282 miles per second. This is not an estimate or an approximation. This is a fundamental constant of the universe, measured and verified to extraordinary precision, the same in every direction, at every location, under all conditions. Light does not accelerate. It does not slow down in empty space. It simply moves at this speed, always, without exception. 186,000 miles per second is difficult to comprehend because nothing in human experience moves this fast. The fastest thing you've encountered, a commercial airplane, travels at roughly 1/6 of a mile per second. Light moves more than 1 million times faster. In 1 second, light travels far enough to circle Earth's equator 7.5 times. In the time it takes you to blink, Light could travel from New York to Los Angeles and back again twice. This is the speed limit of the universe. Nothing moves faster. Nothing can move faster. Accelerate an object with mass toward light speed and its mass increases, requiring more and more energy to push it faster, approaching infinite energy requirements as you approach light speed. The universe forbids it. Light speed is the ceiling, the absolute maximum, the fastest that information or matter or anything can travel through space. And yet, even at this incomprehensible velocity, light takes time to cross cosmic distances. Even moving at the ultimate speed, light doesn't arrive instantaneously. It travels, it crosses space, it accumulates minutes, hours, years on its journey between objects. This is the fundamental revelation that changes how we measure distance in the universe. When gaps become large enough, when space stretches far enough, even light takes measurable time to traverse it. The Moon sits roughly 240,000 miles from Earth. Light covers this distance in 1.3 seconds. When you see the Moon in the sky, you're seeing it as it was 1.3 seconds ago. The light that left its surface reflected from the Sun travelled through empty space for just over 1 second before reaching your eyes. This delay is so brief it's effectively irrelevant. For all practical purposes, you're seeing the Moon in real time. But it's not real time, it's delayed. The Moon you observe is the Moon of the past, albeit the very recent past. This matters more than it seems because it establishes a principle that becomes crucial as distances grow. You never see anything in the universe as it is right now. You only see things as they were when their light began its journey toward you. The universe you observe is a universe of the past, a collection of images from different moments in history, all arriving at your eyes simultaneously, but representing events that occurred at different times. The Sun sits 93 million miles from Earth. Light from the Sun takes 8 minutes and 20 seconds to reach us. When you look at the Sun, you're seeing it as it was 8 minutes ago. If the Sun suddenly vanished, blinked out of existence, ceased to be, you wouldn't know for 8 minutes. You would continue to see it, continue to feel its warmth, continue to orbit around space where it used to be until the last light it emitted completed its journey. Then, 8 minutes and 20 seconds after the Sun disappeared, the sky would go dark. This 8-minute delay between Sun and Earth defines our relationship with our star. Every sunrise you've ever witnessed was actually the sun rising 8 minutes before you saw it rise. Every sunset occurred 8 minutes before the light faded. The sun you observe at noon is the sun of 8 minutes ago. You have never seen the sun as it exists in the present moment. You have only ever seen its past. This delay grows with distance. Mars, at its closest approach, sits 35 million miles from Earth. Light from Mars takes 3 minutes to reach us. If you operated a rover on Mars remotely from Earth, every command you sent would take 3 minutes to arrive. Every image the rover sent back would take 3 minutes to return. You would see the rover as it was 6 minutes ago. Total round-trip delay. If the rover encountered an obstacle, drove toward a cliff, began to tip over, you would watch it happen in the past, helpless to intervene, knowing that by the time you saw the problem and sent a correction, 12 minutes would have elapsed. The rover would have already fallen 6 minutes before your warning arrived. This is why rovers on Mars operate autonomously. Human reaction time becomes useless across interplanetary distances. The speed of light, the fastest possible speed, introduces delays that make real-time control impossible. You can't drive a car from Earth on Mars. You can't pilot a drone. You can't react to changing conditions. The distance is too great. The light speed delay is too long. You can only send instructions, wait for them to arrive, and hope the situation hasn't changed by the time your commands are executed. Jupiter, at 465 million miles, creates a light speed delay of 43 minutes. Saturn requires 90 minutes. Neptune, at its farthest, demands more than 4 hours. When the New Horizons spacecraft flew past Pluto in 2015, the images it captured took 4.5 hours to reach Earth. The mission team watched the flyby happen 4.5 hours after it actually occurred, seeing photos of a world that the spacecraft had already left far behind by the time the first image arrived. This is what light speed delay means in the solar system. Even here, in our immediate cosmic neighbourhood, even among planets that orbit the same star we do, light takes minutes to hours to cross the gaps between worlds. And these are tiny distances by cosmic standards. These are the near distances, the close separations, the gaps that seem small when compared to what lies beyond. Voyager 1, the spacecraft that has travelled farther from Earth than any other human-made object, currently sits roughly 15 billion miles away. Light from Voyager 1 takes 22.5 hours to reach Earth. When engineers send a command to Voyager 1, they must wait 45 hours for a response, 22.5 hours for the signal to arrive, 22.5 hours for the confirmation to return. Nearly 2 full days to have a one-way conversation with a machine that humans built and launched, that's still functioning, still responding, still sending data, but is now so far away that even light struggles to bridge the distance in any reasonable time frame. And Voyager 1 is still in our solar system's extended neighbourhood. It has barely begun to approach interstellar space in any meaningful sense. The real distances, the distances between stars, are so much larger that Voyager's current position seems almost trivial by comparison. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system, 4 light-years away, sitting 4.2 light-years away. A light-year is the distance light travels in 1 year, not 1 day, not 1 month. 1 full year of continuous travel at 186,000 miles per second. 1 light-year equals roughly 6 trillion miles. Proxima Centauri sits 4.2 times that distance from us. 25 trillion miles, give or take. Light from Proxima Centauri takes 4.2 years to reach Earth. When you observe Proxima Centauri through a telescope, you're seeing the star as it was 4.2 years ago. You're seeing light that left that star's surface before the last presidential election, before the pandemic, before whatever major event happened 4 years ago in your personal life. That light has been travelling through empty space this entire time, crossing the vast gulf between stars, moving at the fastest possible speed, and only now arriving at your telescope. This is the closest star to us, the nearest neighbour after our Sun, and it takes light more than 4 years to cross the distance. If something dramatic happened to Proxima Centauri tomorrow, if it exploded or changed or vanished, we wouldn't know until 4.2 years from now. The star you see tonight is the star of the past. The present state of Proxima Centauri is unknown and unknowable. It exists beyond our ability to observe it in real time, separated from us by a distance so great that even light, the fastest thing in the universe, takes years to bridge it. This is why we measure cosmic distance in light years, not because it's convenient or traditional, but because it's the only unit that makes sense. Miles become meaningless. Trillions of miles sound impressive but convey nothing useful. You can't imagine a trillion miles. You can't picture it. The number is too large, too abstract, too disconnected from human experience. But 4.2 light years, while still difficult to grasp, at least provides a framework. It tells you how long light takes to cross the distance. It gives you a sense, however imperfect, of the scale involved. And 4.2 light years is nothing. It's the nearest star, the easy example, the close neighbour. Most stars in our galaxy are hundreds or thousands of light years away. The galaxy itself is 100,000 light years across. Light takes 100,000 years to travel from one side of the Milky Way to the other. 100,000 years moving at 186,000 miles per second, never slowing, never stopping, never deviating, and still requiring a duration longer than anatomically modern humans have existed on Earth just across a single galaxy. This is where distance stops being something you can cross and becomes something you measure. You don't travel light years, you can't. Even if you could somehow accelerate to light speed, which you can't, the journey would still consume years of your life, centuries for distant stars, millennia for the far side of the galaxy. Time becomes the barrier, not speed. Even with infinite velocity, you would still need time to cover cosmic distances, and you don't have infinite velocity. You have, at best, a fraction of light speed, a small fraction. The fastest spacecraft humans have ever built, the Parker Solar Probe, reaches speeds of roughly 430,000 miles per hour at its closest approach to the Sun. This sounds fast. It is fast by human standards, but it's only 0.06% of light speed. At this velocity, the fastest humans can currently achieve, reaching Proxima Centauri would take 73,000 years, the same duration Voyager 1 would need, the same impossible time frame. Light speed isn't just fast, it's the minimum speed necessary to make cosmic travel theoretically possible within human lifetimes, and we can't reach it. We can't even come close. This is the fundamental problem of cosmic distance. The universe is structured at a scale that requires light-speed travel to navigate, but physics forbids anything with mass from reaching light speed. The two facts work together to create a cosmos that is, for practical purposes, untraversable. You can see distant objects because light from them reaches you, but you cannot go to them because you cannot move as fast as light. Distance becomes time, becomes history, becomes limitation. What you see is the past. What you could reach, if you somehow travelled at impossible speeds, would still cost you years or centuries. And what lies beyond even that, what sits too far for light to have reached Earth in the entire history of the universe, remains forever unknown. Not just unvisited, unknown, invisible. Separated from you by distances so vast that information from those places hasn't had time to arrive yet. Let's look at those distances. Let's see what happens when we expand beyond nearby stars and consider the true scale of the galaxy, the structure within which our Sun exists as a single unremarkable point of light among hundreds of billions of others. Before we leave our Sun behind and venture toward other stars, we need to understand where our solar system actually ends. This seems like a simple question with an obvious answer, but it's not. The solar system doesn't have a clear edge, a defined border, a line in space where the Sun's influence stops and interstellar space begins. Instead, it fades gradually. Cheng, Cheng, Di-Jin, transitioning through regions of decreasing influence until finally, at some unclear point far from the warmth and light we know, you've left the Sun's domain entirely. Most people think the solar system ends at Pluto. This makes intuitive sense. Pluto was once considered the 9th planet, the outermost world, the final marker before empty space. But Pluto orbits at an average distance of 3.7 billion miles from the Sun. Light from the Sun takes 5.5 hours to reach Pluto. This seems far. It is far by any human measure, but it's nowhere near the actual boundary of the solar system. Beyond Pluto lies the Kuiper Belt, a region of icy bodies and debris extending from roughly 30 astronomical units to 50 astronomical units from the Sun. An astronomical unit, abbreviated AU, is the average distance from Earth to the Sun, roughly 93 million miles. Astronomers use this unit for solar system distances because it's more manageable than constantly writing out millions or billions of miles. Pluto sits at roughly 40 astronomical units. The Kuiper Belt extends to 50 astronomical units, perhaps slightly beyond. Light takes nearly 7 hours to reach the outer edge of the Kuiper Belt. But the solar system continues. Beyond the Kuiper Belt lies the scattered disk, a region of objects with highly elliptical orbits, extending perhaps to 1,000 astronomical units from the Sun. These objects were scattered outward by gravitational interactions with the giant planets billions of years ago, flung into distant orbits that carry them far beyond the plane where the planets reside. Light from the Sun takes more than 5 days to reach objects at 1,000 astronomical units. 5 days of travel at light speed. The Sun at this distance provides no meaningful warmth. It appears as a bright star, brighter than any other star in the sky, but still just a point of light. The solar system here is dark and cold, a realm of frozen rock and ice drifting slowly through the void. And still the solar system extends farther, much farther. Surrounding the Sun at enormous distance, perhaps as far as 100,000 astronomical units, lies the Oort cloud, a theoretical spherical shell of icy objects that represents the true outer boundary of the Sun's gravitational influence. The Oort cloud has never been directly observed. It's too far away, its objects too small and dark to see with current telescopes. We know it exists because long-period comets that take thousands or millions of years to orbit the Sun, must originate somewhere, and their orbital characteristics suggest they come from a distant reservoir of icy bodies surrounding the solar system. 100,000 AU is roughly 1.6 light-years from the Sun. Light from the Sun takes more than a year and a half to reach the inner edge of the Oort cloud. If you stood on an object in the Oort cloud and looked back toward the Sun, you would see it as it was more than a year ago. You would be so far from the source of light and warmth that sustains life on Earth that the Sun would appear as nothing more than an unusually bright star among all the other stars, indistinguishable except by familiarity. This is the solar system, not the neat arrangement of planets you see in textbooks, not the orderly procession from Mercury to Neptune, but a vast sphere of influence extending more than a light year from the Sun in all directions, filled mostly with darkness and ice and objects we've never seen and probably never will see. When we say our solar system, we usually mean the planets, the familiar worlds that orbit relatively close to the Sun. But the true solar system, the full extent of the Sun's gravitational domain, is incomparably larger than the region where planets exist. Voyager 1, travelling for 47 years, has covered roughly 160 astronomical units. It has passed through the Kuiper Belt, passed through the scattered disk, and entered what scientists call the heliopause, the boundary where the solar wind from the Sun meets the interstellar medium. This is sometimes described as leaving the solar system, and in one sense it's accurate. Voyager 1 is no longer within the bubble of charged particles flowing outward from the Sun. It's in interstellar space, technically beyond the Sun's immediate influence. But it hasn't reached the Oort cloud. It won't reach the Oort cloud for another 300 years, and it won't exit the Oort cloud, won't truly leave the solar system's gravitational boundary for another 30,000 years. 30,000 years of travel at 38,000 miles per hour to cross the full diameter of the Sun's domain. This is the distance we're discussing. This is the scale of the region surrounding a single star, and our Sun is not special. Every star has a similar region of influence, a zone where its gravity dominates, where objects orbit and debris accumulates. Every star sits at the centre of its own bubble of space, separated from other stars by distances vastly larger than the size of the bubbles themselves. The gaps between stars aren't just empty space, they're enormous gulfs, voids so wide that even light takes years to cross them, distances that make the solar system's already incomprehensible size seem trivial by comparison. Proxima Centauri sits 4.2 light-years away. The Oort cloud extends roughly 1.6 light-years from the Sun. If you imagine the Sun's sphere of influence as a bubble extending to the edge of the Oort cloud, and you imagine Proxima Centauri surrounded by a similar bubble, the two bubbles still don't touch. There's still a gap between them, a space of roughly 1 light-year where neither star's gravity dominates, where interstellar space truly begins. The stars don't sit adjacent to each other like houses on a street. They're separated by distances far greater than their own regions of influence, isolated islands in an ocean of darkness. This isolation is fundamental to understanding cosmic distance. Stars aren't packed together, they're not crowded. The galaxy contains hundreds of billions of stars, and yet the average distance between them is so vast that most of space, even within the galaxy, is empty. The stars you see in the night sky, the ones that appear to cluster and form patterns, are actually separated by light-years of nothing. They look close because they're all far away, and distance at that scale flattens perspective, makes everything seem equidistant. But they're not close, they're isolated, each one surrounded by its own vast territory, unreachable from their neighbours except by light. Travel between stars isn't like travel between planets. It's not a matter of waiting months or years in a spacecraft. It's a fundamental challenge that current technology cannot address. The distances are too large, the speeds required are too high, the time needed exceeds human lifespan by factors of hundreds or thousands. When you look at the nearest star and try to imagine reaching it, you're not imagining a difficult journey, you're imagining an impossible one. Unless something changes, unless speed increases dramatically, unless we develop propulsion systems that can reach significant fractions of light speed, the stars remain out of reach. We can observe them, we can study their light, we can learn about their composition, their age, their planets, but we cannot go to them. The distance forbids it, and these are the near stars, the close neighbours, the ones within a few light-years of our Sun. Most stars in the galaxy are not this close. Most stars are hundreds, thousands, tens of thousands of light-years away. The galaxy itself, the Milky Way, is a disk roughly 100,000 light-years across and 1,000 light-years thick. Our Sun sits about 26,000 light-years from the galactic centre, embedded in one of the spiral arms, surrounded by other stars but separated from them by distances that make even Proxima Centauri seem close. 26,000 light-years to the centre of our own galaxy. If you could somehow travel at light speed, the journey would take 26,000 years. You would leave Earth now, at light speed, the fastest possible velocity, and you would arrive at the galactic centre around the time humans first developed agriculture. The entire span of recorded human history could fit into the journey multiple times. Civilizations could rise and fall, technologies could be invented, perfected, and forgotten, and you would still be travelling, still crossing the distance, still years or centuries away from arrival. But you can't travel at light speed. You can manage, optimistically, perhaps 10% of light speed with hypothetical future technology. At 10% light speed, the journey to the galactic centre takes 260,000 years. Longer than anatomically modern humans have existed. Longer than any human civilization has persisted. Longer than any meaningful measure of human time. This is the galaxy. This is the structure we inhabit. The collection of stars we call home. And it's so vast that crossing it, even with technology we can barely imagine, would take longer than our species has existed. The stars at the far side of the galaxy, the ones orbiting 100,000 light years from our position, might as well be in another universe. The light from them takes 100,000 years to reach us. Anything we see from those stars is 100,000 years old. The stars themselves might not even exist anymore. They might have died, exploded, faded away, and we wouldn't know because the light from their deaths hasn't reached us yet. Distance at this scale becomes history. The farther you look, the further back in time you see. The galaxy you observe is not the galaxy as it exists now, but the galaxy as it existed at different points in the past, all layered together into a single image. The near stars you see as they were a few years ago, the distant stars as they were thousands or tens of thousands of years ago, the galactic centre as it was 26,000 years in the past. You're seeing a historical document, a record of what was, not what is. And this is just our galaxy. One galaxy among hundreds of billions. One island of stars in a universe filled with such islands, separated from each other by distances that make interstellar space look crowded by comparison. The gaps between galaxies are measured in millions of light years. The journey from our galaxy to the nearest large galaxy, Andromeda, would take 2.5 million years at light speed. 2.5 million years of travel to reach our closest galactic neighbour. Let's look at those distances. Let's see what happens when we step beyond the scale of a single galaxy and try to comprehend the space that separates these vast structures from each other. The galaxy feels like everything. When you look up at the Milky Way on a dark night, when you see that band of light stretching across the sky, you're seeing the combined glow of billions of stars, all of them part of the same gravitationally bound structure, all of them orbiting the same centre. The galaxy seems vast because it is vast. 100,000 light years across, hundreds of billions of stars, more planets than we could ever count. It feels complete, like a universe unto itself. But the galaxy is not the universe. It's a single object within the universe, one structure among countless others, separated from its neighbours by gulfs of space that make interstellar distance seem almost trivial. The space between stars is enormous, yes, measured in light years, requiring centuries or millennia to cross even at speeds we cannot achieve. But the space between galaxies is so much larger that it operates on an entirely different scale of incomprehensibility. The nearest major galaxy to the Milky Way is Andromeda, also called M31, sitting roughly 2.5 million light years from us. 2.5 million light years, not 2.5 light years like the edge of our solar system, not 4.2 light years like Proxima Centauri, 2.5 million light years. The light you see from Andromeda tonight left that galaxy 2.5 million years ago, before modern humans existed, before Homo sapiens emerged as a species, when our ancestors were still primitive hominids using stone tools and learning to control fire. That light has been travelling through empty space for the entire duration of human evolution. It crossed the void between galaxies while our species evolved from early hominids into modern humans, while we developed language and art and culture and civilization. It travelled while we built cities, invented writing, discovered agriculture, developed technology. Every moment of recorded human history occurred while this light was in transit, crossing the gap between Andromeda and the Milky Way. And now it arrives. Now it reaches your eyes, allowing you to see a galaxy as it was in the distant past. A collection of hundreds of billions of stars whose current state is unknown and unknowable. You cannot see Andromeda as it exists right now. You can only see it as it existed 2.5 million years ago. The galaxy might have changed. Stars might have been born or died. Supernovae might have detonated. Planets might have formed or been destroyed. None of these changes are visible to you yet because the light from them hasn't arrived. It's still crossing the void, still travelling, still years or centuries or millennia away from reaching Earth. 2.5 million light-years is a distance that human minds cannot properly comprehend. You can write the number, you can say the words, but you cannot picture it. You cannot hold it in your imagination. The scale exceeds every reference point you have. Walking wouldn't just take forever. It would take so long that forever becomes meaningless. Spacecraft travelling at current maximum speeds wouldn't arrive within any time frame that connects to human civilization, or human existence, or even human evolution as a species. At light speed, the absolute maximum possible velocity, the journey to Andromeda would take 2.5 million years. You would leave Earth now, travelling at the speed of light, and you would arrive at Andromeda around the time our ancestors were learning to make simple stone tools. The entire development of humanity would occur during your journey. You would miss all of it. You would travel through darkness while our species evolved, while we spread across the planet, while we built everything we've ever built. And when you finally arrived, when you finally reached Andromeda after 2.5 million years of travel, everyone you knew would have been dead for millennia. The civilization you left would be unrecognizable or gone entirely. The Earth itself would have changed in ways you couldn't predict. But you cannot travel at light speed. You can manage, with tremendous optimism about future technology, perhaps 10 or 20% of light speed. At 10% of light speed, the journey to Andromeda takes 25 million years. At 20% it takes 12.5 million years. These numbers stop having meaning. They're too large to connect to anything human. They exceed geological timescales. They approach the age of some species. They represent durations so long that they blur into abstraction. And Andromeda is our nearest major galactic neighbour. It's the close one, the easy example, the galaxy we use when we want to discuss intergalactic distance, without overwhelming people with incomprehensible numbers. Most galaxies are much farther away, billions of light years distant, so far that their light has been travelling toward us since before Earth existed, since before the Sun formed, since the universe was young and stars were just beginning to coalesce from clouds of hydrogen gas. But let's stay with Andromeda for a moment longer because something important is happening between our galaxy and theirs. Andromeda is not sitting still in space. Neither is the Milky Way. Both galaxies are moving, drawn together by mutual gravitational attraction, falling toward each other across the void. The distance between them is shrinking. Slowly, yes, but measurably. Andromeda is approaching the Milky Way at roughly 68 miles per second. 68 miles per second sounds fast. It's roughly 245,000 miles per hour. If you could travel this fast, you could circle Earth in less than 2 hours. It's faster than any spacecraft humans have built. It's a speed that would seem miraculous if you could harness it. But across intergalactic distances, 68 miles per second is glacially slow. At this rate of approach, Andromeda and the Milky Way will collide in approximately 4 billion years. 4 billion years! The collision is inevitable. The galaxies are falling toward each other, and nothing will stop them. In 4 billion years, they will meet. They will pass through each other, their stars intermingling, their gas clouds colliding and triggering new waves of star formation. The two galaxies will merge, becoming a single larger galaxy, a new structure born from the fusion of two enormous collections of stars. And all of this will happen over the course of millions of years, a slow-motion collision that plays out across timescales humans cannot witness. But 4 billion years is so far in the future that it has no relevance to human existence. The Sun will die before then. Earth will become uninhabitable long before Andromeda arrives. Our species, if it still exists, will have evolved into something unrecognizable, or spread to other star systems or gone extinct. The collision between the Milky Way and Andromeda is a cosmological certainty, but it's a certainty that belongs to a future so distant it might as well be a different universe. This is what intergalactic distance creates, not just spatial separation, but temporal separation. Events are so far away that they unfold across timescales longer than species exist, longer than planets remain habitable, longer than stars burn. You can observe these events through light that arrives from the distant past, but you cannot participate in them. You cannot influence them. You can only watch, knowing that what you see has already happened, that the outcome is already determined, that the light showing you the event is just the news arriving late from something that finished long ago. Between the Milky Way and Andromeda lies mostly empty space. Not completely empty, there are smaller galaxies in the region, dwarf galaxies with fewer stars, irregular clumps of matter orbiting or drifting between the two larger structures. But mostly it's void. 2.5 million light-years of nothing. No stars except those belonging to one galaxy or the other. No planets. No gas clouds dense enough to form new stars. Just emptiness, dark and cold, stretching across distances that light takes millions of years to cross. This is intergalactic space. This is what separates the islands of stars from each other. And our local group, the cluster of galaxies that includes the Milky Way and Andromeda, and dozens of smaller galaxies, is unusually crowded by cosmic standards. Most galaxies are farther apart. Much farther. The average distance between large galaxies in the universe is tens of millions of light-years. Some galaxies sit in relative isolation, hundreds of millions of light-years from their nearest neighbours, alone in vast regions of empty space. Light from those distant galaxies takes hundreds of millions of years to reach us. When you observe a galaxy 100 million light-years away, you're seeing it as it was 100 million years ago, before humans existed, before primates existed, when dinosaurs still walked the Earth. The light left that galaxy during the Cretaceous period, travelled through empty space while dinosaurs went extinct, while mammals diversified, while our primate ancestors evolved, while humans emerged and built civilization. And now the light arrives, carrying information about a galaxy that existed in the age of dinosaurs, showing you a snapshot of the distant past. You will never know what that galaxy looks like now. You will never see its present state. By the time light showing the galaxy's current condition reaches Earth, millions of years will have passed. Humans might not exist anymore. Our sun might have changed. Earth might be uninhabitable. The light will arrive to an Earth that has moved on, that has become something different, that may or may not still have observers capable of seeing it. Distance becomes time, becomes history, becomes separation. The farther you look into the universe, the further back in time you see. The more distant the object, the older the light, the more ancient the image. Galaxies billions of light years away appear as they were billions of years ago in the early universe, when stars were younger and galaxies were still forming. You're not seeing the present universe when you look at deep space. You're seeing a historical record, a collection of images from different moments in cosmic history, all arriving simultaneously but representing vastly different eras. And this raises a question. If distance means time, if looking outward means looking backward, how far can you see? How distant is the farthest object whose light has had time to reach Earth? How deep into the past can you look before you reach the limit, the edge, the boundary beyond which no light has yet arrived? The answer involves the age of the universe itself, the expansion of space, and the strange fact that the universe has an edge you can see but never reach. Let's explore that edge. Let's understand what it means to look at the most distant objects in the cosmos and see not just distant space but distant time, not just faraway galaxies but the early universe itself, still visible because its light is only now completing its journey across billions of years of expanding space. Before we can understand the edge of the visible universe, we need to grasp the full scale of a single galaxy. Not the distance between galaxies, but the distance within one. The space that stars must cross if they orbit from one side of the galactic disk to the other. The gulf that separates the spiral arms, the core, the outer halo. The distances that exist within the structure we call home. The Milky Way stretches roughly 100,000 light-years from edge to edge. This measurement represents the diameter of the visible disk, the flattened region where most stars reside, where spiral arms wind outward from the central bulge. 100,000 light-years of space filled with stars, gas, dust, and darkness. At the centre sits a supermassive black hole, 4 million times the mass of our Sun, holding the galaxy together through gravity. Around this centre, hundreds of billions of stars orbit in vast elliptical paths, some taking hundreds of millions of years to complete a single revolution. Our Sun sits approximately 26,000 light-years from this centre, embedded in what astronomers call the Orion Spur, a minor spiral arm branching off from the larger Perseus arm. From this position, the Sun orbits the galactic centre at roughly 500,000 miles per hour. This sounds fast, and it is fast by human standards, but the distance is so enormous that completing one full orbit takes approximately 230 million years. This duration is called a galactic year, though it's not a year by any conventional meaning. It's the time needed for our solar system to travel all the way around the galaxy and return to roughly the same position. 230 million years. The last time our Sun was at this point in its orbit, dinosaurs had not yet evolved. Reptiles were just beginning to dominate the land. The continents existed in different configurations. Earth was a different planet. And since then, the Sun has carried us once around the galaxy, through spiral arms and voids, past countless other stars, traversing distances so vast that even moving at 500,000 miles per hour requires geological timescales to cross them. Think about what this means. The Sun has orbited the galactic center roughly 20 times since it formed 4.5 billion years ago. Only 20 orbits in the entire lifetime of our solar system. Each orbit represents a span of time so long that entire eras of Earth's history fit within it. The formation and extinction of species, the rise and erosion of mountain ranges, the opening and closing of oceans, all of this occurs while the Sun slowly, impossibly slowly from a human perspective, circles the center of the galaxy. If you wanted to travel from our position to the galactic center, moving at light speed, the journey would take 26,000 years. Not 26 years, 26,000 years. You would leave Earth now travelling at the fastest possible speed, and you would arrive at the galactic core around the time humans first painted on cave walls, first buried their dead with ceremony, first began to create art and ritual. The entire span of human civilization, everything we've built and discovered and achieved, would fit comfortably within the travel time to the centre of our own galaxy. At 10% of light speed, a velocity we cannot currently achieve but might theoretically reach with future technology, the journey takes 260,000 years. This exceeds the entire existence of Homo sapiens as a species. You would leave Earth as a modern human and arrive at the galactic centre long after modern humans had evolved into something else or gone extinct entirely. The distance is so vast that even travelling at tremendous speeds, even moving faster than anything humans have ever built, the journey would outlast our species. And the galactic centre is not even the farthest point in our galaxy. Stars exist in the outer halo, in the extended regions beyond the visible disk, at distances approaching 75,000 light-years from Earth. Light from these stars takes 75,000 years to reach us. When you observe one of these distant stars through a telescope, you're seeing it as it was when Neanderthals still existed, when modern humans were just beginning to spread out of Africa, when the last ice age was approaching its peak. The star you observe existed in a universe where humans were primitive, scattered, barely recognizable as the species we would become. And that star is still in our galaxy, still part of the Milky Way, still gravitationally bound to the same structure we inhabit. The distance between us is internal, not intergalactic. It's the space within a single collection of stars, and yet it's so vast that light takes longer to cross it than human civilization has existed. Now consider travelling across the entire diameter of the galaxy. 100,000 light-years from one edge to the other. At light speed, this journey takes 100,000 years. At 10% of light speed, it takes 1 million years. 1 million years of continuous travel to cross from one side of the Milky Way to the other. Civilizations could rise and fall during this journey. Species could evolve. Continents could shift. Ice ages could come and go. The Earth you left would be geologically different from the Earth that existed when you arrived, assuming Earth still existed at all. This is the scale of a galaxy. This is the space enclosed within a single, gravitationally bound structure, one island of stars among hundreds of billions in the universe, and travelling across it, even at speeds we consider impossibly fast, would take longer than our species has existed. The galaxy is not just large, it's large in a way that makes human timescales irrelevant. Our lifetimes, our civilizations, our entire existence as a species represents a tiny flicker within the time it would take to cross from one side of our galaxy to the other. But the galaxy contains structure. It's not a uniform distribution of stars. The density varies. Near the centre, stars are packed more tightly together, with average distances between them shrinking to perhaps 1 light-year or less. In the spiral arms, where star formation is active, clusters of young stars sit relatively close to each other, sometimes separated by less than a light-year. These are the dense regions, crowded neighborhoods where stars exist in something approaching proximity. In the outer regions, in the halo and beyond the visible disk, stars are sparse. The average distance between them grows to tens or even hundreds of light years. Some stars drift alone, separated from their nearest neighbors by gulfs that would take centuries to cross at light speed. These are the isolated stars, the ones that exist at the boundary of the galaxy, barely held by gravity, orbiting slowly in the vast empty spaces that surround the galactic core. And between the spiral arms, in the regions where star density drops, there are voids. Not empty voids, because gas and dust exist everywhere in the galaxy to some degree, but regions where stars are rare, where the darkness dominates, where you could travel for light years without encountering another sun. Our sun passes through these regions during its orbit, spending millions of years crossing the gaps between spiral arms, travelling through relative emptiness before entering the denser regions where new stars are forming. The galaxy is a dynamic structure, not a static one. Stars orbit at different speeds depending on their distance from the centre. The spiral arms rotate, though not as solid objects but as density waves, regions where stars and gas temporarily bunch up before dispersing again. The entire galaxy is in motion, churning slowly, mixing its contents over timescales of hundreds of millions of years. And all of this motion, all of this structure, exists within a space 100,000 light-years across, a distance so vast that observing the far side of the galaxy means seeing it as it was 100,000 years in the past. You cannot see the galaxy as it exists right now. You cannot observe its present structure. When you look at the galactic centre, you see it as it was 26,000 years ago. When you observe stars in the outer halo, you see them as they were tens of thousands of years in the past. The galaxy you see is a composite, a collection of images from different moments in history, all layered together because light from different regions takes different amounts of time to reach you. This creates a strange reality. The galaxy as it exists right now, the present moment structure with all its stars in their current positions, is unknown to you. You can calculate where stars should be based on their motion. You can predict the galaxy's current structure using models and mathematics, but you cannot observe it directly. You can only see the past, the historical record, the light that has finished its journey and arrived at your eyes. And this is just one galaxy, the Milky Way, our home, the structure we inhabit. If understanding its scale, if grasping the distances within it, if comprehending the time required to cross it feels impossible, that's because it is impossible. Human minds did not evolve to understand spaces this large or times this long. We evolved to understand distances we could walk, durations we could experience, scales that mattered to survival on a planet where the horizon was a few miles away and a human lifetime was measured in decades. The galaxy exists on a scale so far beyond human experience that understanding it requires abandoning intuition entirely. You cannot feel these distances, you cannot imagine them properly, you can only describe them using numbers and comparisons, knowing that the numbers are too large to hold meaning, and the comparisons eventually break down under the weight of the scale involved. But we're not done expanding outward. We've discussed the Milky Way, the structure we call home. We've touched on Andromeda, our nearest major galactic neighbour. But the universe contains more than just these two galaxies. It contains hundreds of billions of galaxies, perhaps trillions, spread across distances that make the space between the Milky Way and Andromeda seem almost trivial. The gaps between galaxies grow as you look farther out, as you observe more distant regions of the cosmos, as you approach the edge of what's visible. Let's look at those gaps. Let's see what exists in the spaces between galaxies, and what it means when we say the universe is mostly empty, mostly void, mostly nothing separating tiny islands of light from each other across distances that even light struggles to cross. The space between galaxies is not like the space between stars. When you look at the gap separating our Sun from Proxima Centauri, 4.2 light-years of emptiness, that space is still within a galaxy. It's still part of a larger structure, still governed by the gravitational influence of the Milky Way, still containing trace amounts of gas and dust and the occasional wandering object. It's empty by human standards, yes, but it's not truly void. It's simply sparse, a region where matter exists in concentrations too low to form stars or planets, but high enough to be detectable. Intergalactic space is different. The space between galaxies, the true voids that separate these islands of stars from each other, represents emptiness on a scale that makes interstellar space seem crowded. The average density of matter in intergalactic voids approaches nearly nothing. Perhaps 1 atom per cubic meter, perhaps even less in the deepest voids. For comparison, the air you breathe contains roughly 10 to the power of 25 atoms per cubic meter. The difference between air and intergalactic space is so vast that calling the void empty is almost an understatement. In these voids, there are no stars, no planets, no gas clouds dense enough to collapse and form new stars, no dust, no meaningful radiation except the faint cosmic microwave background that permeates all of space. Just emptiness extending for millions of light years in every direction, separating galaxy clusters from each other, creating gaps so wide that light takes millions of years to cross them, even at its maximum speed. Our local group, the collection of galaxies that includes the Milky Way and Andromeda and dozens of smaller dwarf galaxies, occupies a region roughly 10 million light-years across. This is the neighbourhood, the local environment, the immediate cosmic vicinity. Within this region, gravity binds the galaxies together. They orbit a common centre of mass. They influence each other gravitationally. They will eventually, over billions of years, merge into a single larger structure. The local group is a gravitationally bound system, one unit within the larger universe. Beyond the local group, the nearest significant collection of galaxies is the Virgo cluster, sitting roughly 55 million light-years away. 55 million light-years. The light you see from galaxies in the Virgo cluster left those galaxies 55 million years ago, during the Eocene epoch, when early primates were just beginning to evolve, when the Earth was warmer and ice caps didn't exist at the poles, when the continents were still drifting toward their current positions. That light has been crossing the void ever since, travelling through empty space while the Earth cooled, while primates evolved into apes, and apes into hominids, and hominids into humans. Between the local group and the Virgo cluster lies mostly nothing. Some isolated galaxies exist in the gap, small irregular collections of stars that don't belong to either cluster, but mostly it's void. Tens of millions of light-years of space containing almost no matter, no structure, no objects of significance. Just darkness and distance and the faint trace of atoms scattered so thinly that they might as well not exist. If you stood in the middle of this void, if you could somehow position yourself at the midpoint between the local group and the Virgo cluster, the view would be profoundly isolating. Galaxies would appear as faint smudges in every direction, distant and dim, separated from you by millions of light-years. The nearest galaxy might be 10 or 20 million light-years away. You would be alone in a way that's difficult to articulate, surrounded by emptiness so complete that the word empty feels insufficient. No stars, no light except the ancient glow of distant galaxies. No destinations within reach, just void extending in all directions for distances that light takes millions of years to cross. This is what the universe is mostly made of. Not stars, not galaxies, not planets or gas clouds or dust. Empty space, voids, gaps so large that galaxies, objects containing hundreds of billions of stars, appear as tiny isolated structures separated by distances that dwarf their own size. When you look at images of the deep universe, images showing thousands of galaxies scattered across the field of view, what you're seeing is a tiny fraction of the total volume. Most of the universe is the empty space between those galaxies, the voids that don't show up in photographs because there's nothing there to emit light. Astronomers have mapped the large-scale structure of the universe, plotting the positions of millions of galaxies to understand how they're distributed through space. What they've found is that galaxies cluster together in filaments and walls, long strings of galaxy clusters connected to each other, forming a web-like pattern across cosmic scales. Between these filaments lie enormous voids, regions hundreds of millions of light-years across containing almost no galaxies, almost no matter, almost nothing. These voids are the dominant feature of the universe's structure. The galaxies exist on the edges, clustered along the boundaries, while the interiors remain empty. The largest known void, the Bhuta's void, stretches roughly 330 million light-years across. 330 million light-years of nearly empty space, containing perhaps 60 galaxies in a volume that should, based on average cosmic density, contain thousands. Light takes 330 million years to cross this void. When you observe the far side of the Bhuta's void, You're seeing it as it was before dinosaurs existed, before complex life on land, when Earth's oceans were full of primitive fish and the continents were still forming. Crossing this void, even at light speed, would take longer than complex life has existed on Earth. At 10% of light speed, it would take 3 billion years, roughly the time since the first photosynthetic organisms began producing oxygen in Earth's atmosphere. The void is so large that travelling across it at speeds we consider incredibly fast would outlast the existence of entire biospheres, entire evolutionary lineages, entire planetary ecosystems, from formation to potential extinction. And the void is just empty space. There's no reason to cross it. No destinations within it worth reaching. It's simply there, a gap in the cosmic web, a region where the universe decided not to put much matter. But its existence, its enormous scale, tells you something important about the universe itself. The cosmos is not dense. It's not packed with galaxies and stars and planets all crowding together. It's overwhelmingly empty, with matter concentrated in a tiny fraction of the total volume, clustered along the edges of vast voids that contain almost nothing. When you look at the night sky, you see stars. You see the Milky Way stretching overhead, a band of combined starlight that represents billions of distant suns. The sky seems full, populated, rich with objects. But this is an illusion created by your position within a galaxy. You're standing inside one of the rare regions where matter concentrated, where stars formed, where planets could exist. If you could step outside the galaxy, float in intergalactic space, the sky would change dramatically. Stars would vanish. The Milky Way would appear as a distant smudge, one galaxy among countless others, all of them separated by vast distances. The sky would be almost completely dark, filled with faint galaxies but devoid of individual stars because stars only exist within galaxies, and you would be outside all of them, alone in the void. This darkness, this emptiness, is the default state of the universe. Matter is rare, structure is rare, galaxies are rare. Most of space is void, and the voids are growing. The universe is expanding, and as it expands, the distances between galaxy clusters increase. The voids grow larger, the gaps widen. Galaxies that are not gravitationally bound to each other drift apart, carried by the expansion of space itself, moving farther and farther from each other as time passes. This expansion means that the universe you observe today is more spread out than it was yesterday, and tomorrow it will be more spread out than it is today. The distances between galaxy clusters grow continuously. The voids expand. The universe becomes emptier, more sparse, more isolated. Billions of years from now, if any observers still exist, they will see a lonelier cosmos than we see now. Fewer galaxies will be visible. More of them will have drifted beyond the horizon, their light redshifted to invisibility by the expansion of space. The universe will be darker, quieter, more empty than it is today. But even now, even in the present moment, the universe is already overwhelmingly empty. The matter you see, the stars and galaxies and planets, represents a tiny fraction of the total volume. Most of the universe is void. Most of space contains nothing. Most of the cosmos is darkness punctuated by rare islands of light separated by distances so vast that light itself takes millions or billions of years to cross them. And this raises the question of limits. If the universe is expanding, if distances are growing, if galaxies are moving apart, how far can you see? How distant is the farthest galaxy whose light has reached Earth? How deep into the universe can you look before you reach the edge, the limit, the boundary beyond which no light has yet arrived? The answer involves not just distance, but time, not just space, but the history of the universe itself, and the strange fact that the edge you can see is not the edge that exists. Let's examine that edge. Let's understand what it means to look at the most distant objects in the cosmos and see not just space, but time, not just galaxies, but the early universe, still visible because its light is only now completing its journey across billions of years of expanding space. The universe has an age. This is one of the most important facts in cosmology, and it changes everything about how we understand cosmic distance. The universe began roughly 13.8 billion years ago in an event we call the Big Bang. Before this moment, there was no space, no time, no matter, no energy. Everything that exists, everything you can see or touch or measure, emerged from this beginning. And because the universe has a finite age, because it has only existed for a specific duration, light has only had a finite amount of time to travel. This creates a limit, a boundary, a horizon beyond which you cannot see, not because the universe ends there, but because light from regions beyond that horizon hasn't had enough time to reach you yet. The farthest you can possibly see is determined by how far light can travel in 13.8 billion years. This distance defines what astronomers call the observable universe, the sphere of space surrounding Earth from which light has had time to arrive since the beginning. But 13.8 billion light-years is not the radius of the observable universe. It should be, if you use simple logic. If the universe is 13.8 billion years old, then light has had 13.8 billion years to travel, which means it should have covered 13.8 billion light-years. But the universe has been expanding during all that time. The space through which light travels has been stretching, growing, increasing in size while the light moves through it. A photon that left a distant galaxy shortly after the Big Bang has been travelling for nearly 13.8 billion years, but the space between its starting point and Earth has expanded during its journey. The galaxy that emitted the photon is now much farther away than 13.8 billion light-years. The current radius of the observable universe is approximately 46.5 billion light-years. This is the distance to the farthest objects whose light is reaching us right now, the galaxies that existed in the early universe and emitted light that has been travelling toward us ever since. Those galaxies are now 46.5 billion light-years away due to the expansion of space, even though their light has only been travelling for 13.8 billion years. The numbers don't match because the distance has grown while the light was in transit. 46.5 billion light-years. This is the edge of the observable universe, the horizon beyond which you cannot see, because light from farther regions hasn't had time to reach you yet. Everything you can observe, every galaxy you can detect with telescopes, every structure in the cosmos that's visible from Earth, lies within this sphere, and everything beyond it is unknown. Not because it doesn't exist, but because its light hasn't arrived yet. When you observe the most distant galaxies, the ones at the edge of the observable universe, you're seeing them as they were more than 13 billion years ago, when the universe was young, when stars were just beginning to form, when galaxies were smaller and denser and structured differently than they are now. The light from these galaxies has been travelling toward you for almost the entire age of the universe. It left them when they were young, when the cosmos was less than 1 billion years old, and it has been crossing expanding space ever since, redshifted by the expansion, stretched to longer wavelengths, carrying information about the early universe. These distant galaxies do not look like the Milky Way or Andromeda. They're smaller, more irregular, more chaotic. Star formation within them occurs at rates far higher than in modern galaxies. They're bright in ultraviolet light, dimmer in visible wavelengths, glowing with the energy of young massive stars that burn hot and die quickly. You're seeing galaxies in their infancy, galaxies that have had billions of years to evolve since the light you're observing left them. The galaxies as they exist right now, in the present moment, are unknowable. You can only see their past, the moment when they emitted the light that's just now arriving at Earth. And this past is ancient. The most distant galaxies observed were formed when the universe was only a few 100 million years old. The light you see from them has been travelling for more than 13 billion years. It crossed a universe that was smaller when it started, that expanded while it travelled, that grew larger and cooler and more diffuse as the light moved through it. The photons that left those galaxies experienced the entire history of the universe during their journey. They travelled while stars formed and died, while galaxies merged and evolved, while the cosmos expanded and cooled and structured itself into the web-like pattern we observe today. When that light finally arrives at your telescope, when you capture it and analyse it and study the information it carries, you're looking at a snapshot from the early universe. You're seeing what galaxies looked like billions of years ago. You're observing the cosmos in a state that no longer exists, that transformed long ago into something different, that evolved into the universe we inhabit now. The edge of the observable universe is not a spatial edge, it's a temporal edge. It's the limit of how far back in time you can see, the boundary where the universe was so young that no stars had yet formed, where only hydrogen and helium existed, where the cosmic microwave background was emitted. The cosmic microwave background, often abbreviated as CMB, is the oldest light in the universe. It was emitted roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form, when photons could finally travel freely without being scattered by charged particles. Before this moment, the universe was opaque, a hot, dense plasma that light couldn't penetrate. After this moment, the universe became transparent, and photons from that era have been travelling through space ever since, stretched by expansion into microwave wavelengths, arriving at Earth from all directions as a faint background glow. This is the true edge of the observable universe, not a galaxy, but the cosmic microwave background, the relic radiation from the early universe, the oldest light that exists. When you observe the CMB, you're seeing the universe as it was 380,000 years after the Big Bang. You cannot see farther back than this because before this moment, the universe was opaque. Light did not travel freely. There is no earlier light to observe. The CMB represents the absolute limit of how far you can see into the past. The CMB comes from all directions simultaneously. It surrounds you. It's not coming from a single point or a single region, but from the surface of last scattering, the spherical shell of space that was 380,000 years old when it emitted the light that's just now reaching you. This surface is now roughly 46 billion light years away in all directions due to the expansion of space. You're at the center of the observable universe, not because you're special or because Earth occupies a privileged position, but because the observable universe is defined by your location. It's the sphere of space from which light has had time to reach you. An observer in a distant galaxy would see a different observable universe, centered on their location, with a different set of galaxies at the edge. This creates a strange reality. The observable universe is not the entire universe, it's just the part you can see from Earth. Beyond the edge lies more universe, more galaxies, more structure, but you cannot observe it because light from those regions hasn't reached you yet. The universe beyond the observable horizon might be infinite. It might extend forever in all directions, filled with galaxies and stars and planets and structures identical to what you can see, or it might be different in ways you cannot predict. You have no way of knowing because you cannot see it. The light hasn't arrived. And some of that light will never arrive. This is the strange consequence of expansion. The universe is not just expanding, it's accelerating. The rate of expansion is increasing over time, driven by something astronomers call dark energy, a mysterious component of the universe that causes space itself to expand faster and faster. Because of this acceleration, there are galaxies beyond a certain distance whose light will never reach Earth. Not because they're too far away right now, but because the space between them and Earth is expanding faster than light can cross it. These galaxies are receding from us at speeds greater than the speed of light, carried away by the expansion of space, moving beyond the horizon into regions we will never be able to observe. The edge of the observable universe is not static, it's growing. Every second, light from slightly more distant regions reaches Earth, expanding the sphere of space you can observe. But simultaneously, galaxies at the edge are being carried away by expansion, some of them accelerating beyond the horizon, disappearing from view forever. The observable universe is dynamic, changing, growing in one sense and shrinking in another, expanding as light arrives from farther regions but losing galaxies at the edge as they recede beyond the reach of observation. This is the ultimate limit of cosmic distance. Not the distance to nearby stars or planets or even galaxies, but the distance to the edge of what's observable, the horizon beyond which no information can reach you, the boundary that separates the universe you can see from the universe that exists but remains forever hidden. And this boundary is not a physical edge. It's a consequence of time and expansion, a limit imposed by the finite age of the universe and the accelerating growth of space. You cannot cross this boundary. You cannot travel to the edge of the observable universe and see what lies beyond. Even if you could somehow travel at light speed, the expansion would carry the edge away from you faster than you could approach it. The horizon would recede, always remaining the same distance ahead, always unreachable. Distance at this scale is not something you can overcome with speed or technology. It's a fundamental limit built into the structure of space-time itself. Let's examine this more closely. Let's understand what it means for space to expand, for distances to grow, for galaxies to recede from each other not because they're moving through space, but because space itself is stretching. carrying them apart, creating distances that grow even as you watch. Space is not static. This is difficult to accept because everything in human experience treats space as fixed, as a stage on which objects move but which itself remains unchanging. You walk through space, you drive through it. Objects move from one location to another, but the space between locations stays the same. A mile is always a mile. The distance between two cities doesn't change unless someone moves one of the cities. Space in human experience is stable, but the universe doesn't work this way. Space itself is expanding, not the objects in space moving apart through a fixed background, but the actual fabric of space growing, stretching, increasing in size. The distance between galaxies that aren't gravitationally bound to each other increases over time, not because the galaxies are moving through space, but because new space is appearing between them. The metric of space is changing, the scale is growing, the universe is getting larger. This expansion was discovered in the 1920s when astronomer Edwin Hubble observed that distant galaxies were receding from Earth, and the farther away a galaxy was, the faster it appeared to be moving. This relationship, now called Hubble's law, showed that the universe is expanding uniformly. Every galaxy sees every other unbound galaxy moving away from it. There's no center to the expansion, no point from which everything is moving outward. Instead, space itself is growing everywhere simultaneously, and the more space exists between two objects, the faster the distance between them increases. The current rate of expansion is approximately 67 kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light-years. This means that for every 3.3 million light-years of distance between two objects, the space between them is growing at 67 kilometers per second. A galaxy 3.3 million light-years away is receding at 67 kilometers per second. A galaxy 6.6 million light-years away is receding at 134 kilometers per second. A galaxy 33 million light-years away is receding at 670 kilometers per second. This rate seems small at first. 67 kilometers per second is fast by human standards, roughly 150,000 miles per hour. But it's not extreme compared to the speeds we've already discussed. But the key is that this rate applies per megaparsec of distance. The farther away an object is, the more megaparsecs of space lie between you and it, and therefore the faster it recedes. At large enough distances, the recession velocity exceeds the speed of light. This sounds impossible. Nothing can move faster than light. This is a fundamental rule of physics, confirmed by countless experiments, built into the structure of relativity. But galaxies can recede faster than light because they're not moving through space. Space itself is expanding, carrying them along. The speed limit applies to motion through space, not to the expansion of space itself. Space can expand at any rate. There's no cosmic speed limit on the growth of the metric. Galaxies roughly 14 billion light-years away are receding from Earth at the speed of light. This is called the Hubble sphere, the boundary where recession velocity equals light speed. Galaxies beyond this distance are receding faster than light. You can still see some of them because the light they emitted in the past when they were closer has had time to reach you. But light emitted by those galaxies now will never reach Earth. It's travelling toward you through space, but space is expanding faster than the light can cross it. The light makes progress, yes, but the distance to cross grows faster than the light can travel. It's like trying to swim against a current that's faster than you can swim. You move forward relative to the water, but the current carries you backward faster than you advance, and you never make progress toward your destination. This means there are galaxies you can see right now whose current light will never reach you. You're seeing them as they were in the past, when they were closer, when the space between them and Earth was smaller, and light could still make the journey. But those galaxies have been carried by expansion to distances where new light from them cannot reach you anymore. They're receding too fast. The expansion has outpaced the light. They're fading from view, not because they're dying or dimming, but because the universe's expansion is carrying them beyond the horizon of what's observable. And this process is accelerating. The expansion rate is not constant. It's increasing over time. This acceleration was discovered in the late 1990s, when astronomers observed distant supernovae and found they were farther away than they should be, based on a universe expanding at a constant rate. The universe wasn't just expanding. It was expanding faster and faster, accelerating under the influence of dark energy, a mysterious component that makes up roughly 68% of the universe's total energy density, but whose nature remains unknown. Dark energy acts like a repulsive force, pushing space apart, causing the expansion to accelerate. The more space exists, the more dark energy exists, and the faster the expansion becomes. This creates a feedback loop. Expansion creates more space. More space contains more dark energy. More dark energy accelerates expansion further. The rate of expansion grows exponentially, doubling every 10 billion years or so, carrying galaxies apart at ever-increasing speeds. This acceleration has profound implications for the future of the universe. Galaxies that are not gravitationally bound to our local group will eventually recede beyond the horizon. Their light will redshift into invisibility. They will disappear from view, not because they have been destroyed, but because the space between them and us has grown so large and is growing so fast that light can no longer cross it. Billions of years from now, an observer in the Milky Way will see a much emptier universe. Most galaxies will have vanished beyond the horizon. Only the local group will remain visible, a small cluster of gravitationally bound galaxies surrounded by darkness. Trillions of years from now, if the expansion continues accelerating, even the local group will have merged into a single large galaxy, and that galaxy will be alone in an observable universe that contains no other galaxies, no other structures, nothing but the faint glow of the cosmic microwave background, stretched and redshifted by expansion into wavelengths so long they're almost undetectable. An observer in that distant future would see a universe that appears empty, a cosmos containing only their own galaxy surrounded by void, with no evidence that other galaxies ever existed. But right now, in the present moment, you can still see those distant galaxies. You can observe structures billions of light years away, galaxies whose light has been travelling toward you for most of the universe's history. The expansion has redshifted their light, stretched it to longer wavelengths, but it hasn't yet carried them completely beyond the horizon. You're living in an era when the universe is still observable, when distant structures are still visible, when the cosmos appears full and rich and populated with galaxies. This era won't last forever. The observable universe is shrinking in a sense, losing galaxies at the edge as they accelerate beyond the horizon, faster than new light from closer regions can expand the observable sphere. The universe you can see is temporary, a brief window in cosmic history when expansion hasn't yet erased most structures from view. Observers in the distant past saw a smaller observable universe because light from distant regions hadn't arrived yet. Observers in the distant future will see a smaller observable universe because expansion will have carried most galaxies beyond reach. You exist in the middle, in a time when the observable universe is at or near its maximum richness, when the most galaxies are visible, when the cosmos appears most full. This is not a special time in any cosmic sense. It's simply when conscious observers happen to exist, when stars are still forming, when planets can still support life, when the universe is old enough to have created complexity but young enough that expansion hasn't yet isolated everything. And this expansion means that distance in the universe is not fixed. The distance to a galaxy is growing. The gap between clusters is widening. The space you measure today is larger than it was yesterday, and smaller than it will be tomorrow. Distance becomes dynamic, changing, increasing at rates determined by how much space already exists and how fast that space is expanding. A galaxy that's 1 billion light years away today will be farther tomorrow, and the day after and every day following, carried away by expansion whether you observe it or not. This creates a profound realization. The universe you observe is not the universe as it exists. You're seeing the past. Yes, we've established that. But you're also seeing distances that no longer match reality. The galaxy whose light is reaching you now is farther away than it appears because space has expanded during the light's journey. The universe has changed while the light was in transit. The present state of distant objects is unknowable because by the time information from them reaches you, they've moved, they've changed, they've been carried farther away by expansion. You cannot know the present state of the universe. You can only know its past, and even that past is incomplete, limited to regions from which light has had time to reach you. The present moment, the now, the current state of all galaxies and structures is fundamentally inaccessible. It exists beyond your ability to observe it, and as expansion continues, As acceleration carries more galaxies beyond the horizon, the fraction of the universe you can observe will shrink. More and more of reality will slip beyond reach, leaving you with less information, fewer observations, a smaller window into the cosmos. This is the ultimate consequence of cosmic distance combined with expansion. Not just that objects are far away, but that they're getting farther. Not just that light takes time to arrive, but that some light will never arrive. Not just that the universe is large, but that it's growing, and the growth is creating barriers to observation that time cannot overcome. There are places in the universe you will never see, not because they're hidden or obscured, but because they're receding too fast. The expansion has already carried them beyond your horizon, and they will never return. Let's examine what this means. Let's understand the implications of living in an expanding universe, where distance grows, where horizons exist, where parts of reality are fundamentally and permanently beyond your ability to observe or reach or ever know anything about. There is a galaxy somewhere in the universe whose light will never reach Earth. Not because the light doesn't exist, not because something blocks it, but because the space between that galaxy and Earth is expanding faster than light can cross it. The photons leave the galaxy travelling toward you at light speed, the fastest possible velocity, making progress through space, crossing distance, moving in your direction. But the space ahead of them is growing. New distance appears between the photon and its destination. The gap widens faster than the photon can close it. The light moves forward, but never arrives. It travels forever through expanding space, always approaching, but never reaching. Caught in a universe that grows faster than anything can cross it. This galaxy exists beyond what astronomers call the cosmic event horizon, a boundary roughly 16 billion light-years away in the current universe, beyond which events happening now will never become observable from Earth, no matter how long you wait. Light emitted by galaxies beyond this horizon is fighting a losing battle against expansion. It makes progress, yes, but the finish line moves away faster than the light approaches. The race is unwinnable. The light will travel for eternity and never arrive. This is different from the observable universe boundary. The observable universe, with its radius of 46 billion light-years, represents the limit of what you can see right now. It includes galaxies whose light was emitted in the distant past and has had time to reach you. But some of those galaxies are now beyond the cosmic event horizon. You can see their ancient light, the photons they emitted billions of years ago when they were closer. But any light they emit now will never reach you. They've crossed the boundary. They've entered the unreachable zone. They're visible only as they were, not as they are, and they will never be visible as they are now. This creates a strange asymmetry in time. You're seeing the past of galaxies that no longer have a future connection to you. The light showing you their history will eventually fade as the last photons they emitted before crossing the horizon finally arrive. After that, nothing. No new information, no updates. Those galaxies will freeze in your observation at whatever moment their last observable light was emitted, and then they'll fade from view entirely as that light redshifts into invisibility. They'll become ghosts, historical remnants, objects that once existed in your observable universe but have been carried away by expansion into permanent isolation. The cosmic event horizon is shrinking. As the universe expands and acceleration continues, this boundary moves closer to Earth. Galaxies that are currently just barely within the event horizon, whose light emitted now can still theoretically reach Earth given infinite time, will cross the boundary. The horizon will contract past them. They'll transition from reachable to unreachable. Every moment more galaxies slip beyond this line, more light becomes unable to complete its journey, more of the universe becomes permanently isolated from observation. In the far future, trillions of years from now, the cosmic event horizon will have contracted to include only the local group, the small cluster of gravitationally bound galaxies that includes the Milky Way and Andromeda. Everything beyond that will be unreachable. An observer at that time will live in a universe where only their local cluster exists within the event horizon. Every other galaxy will have receded beyond reach. Light from them will never arrive. Information about them will be limited to whatever ancient photons completed their journey before the horizon contracted past them. The universe will have become fundamentally smaller from an observational standpoint, not because it collapsed, but because expansion isolated everything. This isolation is not just observational, it's physical. You cannot travel to a galaxy beyond the cosmic event horizon. Even if you could somehow accelerate to the speed of light, even if you could maintain that velocity indefinitely, you would never reach that galaxy. The space between you and it is expanding too fast. You would travel forward at light speed, covering distance, making progress, but the destination would recede faster than you could approach. The gap would widen. You would never arrive. The journey would last forever and never complete. This is the ultimate meaning of cosmic distance. Not just that space is large, but that it's too large. Not just that objects are far away, but that they're unreachably far. Not just that travel takes time, but that travel is impossible, fundamentally and permanently impossible, forbidden by the expansion of the universe itself. There are destinations you cannot reach, because the universe's growth rate exceeds the maximum speed at which you can travel. The cosmos contains places that are real, that exist, that are made of matter and energy and structure just like everything you can observe, but that are separated from you by barriers that no technology can overcome. And this creates a profound epistemological limit. There are facts about the universe you cannot know, not because they're too complex to understand or too difficult to measure, but because information about them cannot reach you. Light from those regions won't arrive, signals won't propagate, no message, no data, no evidence from beyond the cosmic event horizon will ever cross into your observable sphere. Those regions exist in a state of permanent unknowability. You can theorize about them, extrapolate from what you observe in nearby regions, assume they're similar to the parts of the universe you can see, but you cannot verify, you cannot check, you cannot observe directly. This might seem abstract, a distant concern affecting only the farthest reaches of the cosmos, but it changes what you can claim to know about the universe. When you say the universe, you mean the observable universe, the sphere of space from which light has reached Earth, but the actual universe, the total universe, the complete structure of reality is larger. How much larger, you don't know. It might be slightly larger, extending a bit beyond the observable horizon. It might be infinitely larger, extending forever in all directions, filled with galaxies and structures and clusters identical to what you see, or completely different in ways you cannot imagine. You have no way of determining which is true. The universe beyond the horizon could be radically different from the universe within it. The laws of physics might vary. The distribution of matter might change. Structures might exist that have no counterpart in the observable region. Or everything might be uniform, identical in all directions, with the unobservable universe looking exactly like the part you can see. Both possibilities are consistent with observation. Both are compatible with everything you can measure. You cannot distinguish between them because you cannot observe the regions where the difference would be apparent. This is the final barrier that cosmic distance creates. Not just a limit on travel, but a limit on knowledge itself. The universe is structured in such a way that parts of it are fundamentally beyond your ability to study. The expansion of space creates horizons that information cannot cross. The accelerating growth of the cosmos ensures those horizons will contract, will shrink, will encompass less and less of reality until eventually only a small local cluster remains observable, while the rest of the universe recedes into permanent isolation. You exist in a moment when the observable universe is relatively large, when many galaxies remain visible, when the horizon hasn't yet contracted to its minimum size. But you're also trapped in a time when most of the universe is already beyond reach, when the majority of galaxies exist at distances you cannot travel, when the expansion has already created barriers that separate your local region from most of reality. The cosmos is larger than you can see and mostly inaccessible. You observe a fraction, a sample, a small portion of the total structure, and you must accept that the rest will remain unknown. This should change how you think about distance. It's not just a measure of space, it's a measure of separation, of isolation, of the fundamental disconnection between different parts of reality. Objects separated by large cosmic distances are not just far apart, they're causally disconnected. Events happening now in one location will never influence events in another if the distance between them is large enough. Light from one will never reach the other. Information cannot propagate. Cause and effect cannot operate across the gap. The two regions exist in the same universe in a technical sense, but they're effectively separate universes, unable to interact, unable to exchange information, unable to know about each other. The universe is not a single connected whole. It's a collection of causally connected regions separated by distances that prevent interaction. Your region, the observable universe surrounding Earth, is one such region. But there are others, many others, perhaps infinitely many, spread throughout the cosmos, each one observing a different sphere of space, each one unable to see or reach the others. These regions overlap at their edges where they're close enough, but most of the universe exists in someone's unobservable zone, beyond someone's horizon, separated from someone's ability to ever know about it. And within your own observable region, within the sphere you can theoretically see, most locations are still unreachable. You can observe them because their light has arrived, but you cannot go to them because the distance is too great, the expansion too fast, the journey too long. They're visible but inaccessible, present in your observations but absent from your possible futures. You can study them, learn about them, understand their properties through the light they emit, but you will never visit them, never sample their matter directly, never confirm through physical presence that they're real. This is the reality of living in an expanding universe. Most of it is beyond reach. Most of it will remain beyond reach. The distances are too vast, the expansion too relentless, the barriers too fundamental to overcome. You're confined to a small region, a local bubble, a tiny fraction of the total cosmos, surrounded by structures you can see but not touch. Galaxies you can observe but not visit. A universe that exists but remains mostly inaccessible. And yet, despite this isolation, despite the unreachable horizons and the growing voids and the accelerating expansion, you can still observe. You can still measure. You can still learn about distant structures through the light they send, the information they provide, the glimpses they offer into regions you'll never physically enter. The universe may be mostly beyond reach, but it's not completely hidden. Light crosses the gaps, information arrives, knowledge accumulates. You're isolated, yes, but not blind. Let's consider what this means. Let's think about what cosmic distance, with all its implications and limitations and barriers, tells us about existence, about observation, about what it means to be a small conscious entity trying to understand a universe that vastly exceeds your ability to fully know or experience. You're standing on a planet 8,000 miles in diameter, orbiting a star 93 million miles away, located in a galaxy 100,000 light-years across, which itself sits in a universe where the nearest major neighbouring galaxy is 2.5 million light-years distant, and the edge of the observable cosmos extends 46 billion light-years in every direction. These are the scales that define your position in reality. These are the distances that separate you from everything else that exists. And yet, somehow from this tiny vantage point, you can observe structures at the edge of the universe. You can detect light that has travelled for 13 billion years to reach you. You can measure the properties of galaxies so distant that they're receding faster than light. You can map the large-scale structure of the cosmos, trace the filaments and voids that define how matter is distributed across billions of light-years. You can look back in time to see the universe as it was when it was young, when the first stars were forming, when galaxies were just beginning to coalesce from clouds of hydrogen gas. All of this is possible because light carries information, because photons cross cosmic distances, because the universe is transparent enough that signals can propagate across it. This ability to observe does not diminish the distances involved. The gaps remain vast, the journey times remain impossibly long, the barriers to physical travel remain insurmountable. But observation creates a kind of connection, a thread of information linking you to distant structures, allowing you to know something about them, even though you cannot reach them. The light from a galaxy 10 billion light-years away took 10 billion years to arrive, but it did arrive. It crossed the expanding space between its source and your telescope. It survived the journey, and now it's here, carrying information about a galaxy that existed 10 billion years ago, allowing you to see that galaxy, study it, understand something about its properties and composition and history. This is what makes cosmic distance bearable in a sense. You cannot cross it, but you can bridge it with observation. You cannot visit distant galaxies, but you can see them. You cannot travel to the edge of the observable universe, but you can study objects near that edge through the light they've sent. Distance creates isolation, yes, but not complete isolation. Information still flows, knowledge still accumulates. The universe reveals itself through light, through the electromagnetic radiation that pervades space, through the signals that cross even the largest voids to reach observers capable of detecting them. But this observational connection is fragile and limited. It depends on light having time to complete its journey. It depends on the expansion not carrying objects beyond the cosmic event horizon before their signals arrive. It depends on the universe remaining transparent, on space not filling with obscuring material that blocks the view, and most critically, it depends on observers existing to receive the signals. Light from distant galaxies arrives at Earth, but if Earth had no telescopes, no conscious beings capable of building instruments and studying the cosmos, that light would arrive unnoticed. It would pass through the location where Earth orbits and continue into space, unobserved, its information uncollected. You are that observer? You, specifically, or humanity more broadly, or conscious life in general if it exists elsewhere in the universe. You are the entity receiving the signals, collecting the photons, processing the information, transforming light into knowledge about distant structures. Without observers, the universe would still exist, the distances would still be vast, the galaxies would still shine, but there would be no awareness of these facts. The cosmos would be entirely unconscious of itself, structures existing in isolation with no entity anywhere understanding the whole. This creates a strange kind of significance for observers. You are tiny by cosmic standards, infinitesimally small compared to galaxies and voids and the observable universe itself. Your planet is a speck. Your star is one among hundreds of billions in your galaxy alone. Your galaxy is unremarkable among hundreds of billions of galaxies in the observable universe. By any measure of size or mass or energy, you are negligible, barely worth mentioning in the inventory of cosmic contents, and yet you are the thing that observes. You are the structure that has developed the capacity to collect information about the universe, to study it, to understand it, to know that it's vast and old and mostly empty. The universe has produced, through billions of years of stellar nucleosynthesis and planetary formation and chemical evolution and biological development, entities capable of comprehending it. This seems almost paradoxical. The cosmos is so large that consciousness appears absurdly small by comparison, and yet consciousness is the only thing that knows the cosmos is large. Without awareness, without observation, size itself becomes meaningless because there's nothing to compare it to, nothing to measure it against, nothing to care that it exists. This doesn't make you cosmically important in any objective sense. The universe would function identically without observers. Stars would still fuse hydrogen, galaxies would still orbit their centers, space would still expand. The laws of physics don't require consciousness to operate. But it does suggest that observation, the act of knowing about the universe, represents something unique within it. Most of the cosmos is unconscious matter following physical laws. A tiny fraction has organized itself into structures capable of awareness, capable of studying the whole, capable of understanding that it exists within something vastly larger than itself. You live in a universe where most of reality is beyond your reach, but not beyond your observation. You cannot visit distant galaxies, but you can see them. You cannot travel to the edge of the observable universe, but you can detect light from objects near that edge. You cannot cross the cosmic event horizon, but you can study regions just inside it. The physical barriers are absolute, yes, but the informational barriers are permeable. Light crosses them, data arrives, knowledge accumulates despite the distances involved, and this knowledge changes you. Understanding cosmic distance, truly comprehending the scales involved, creates a shift in perspective that's difficult to articulate, but impossible to reverse once it occurs. The distances are so vast that they make human concerns feel local and temporary. The timescales are so long that they make human history feel brief and recent. The isolation is so profound that it makes Earth feel simultaneously unique as a known harbour of life and insignificant as a single planet among trillions. This perspective doesn't diminish human experience. Your life still matters to you. Your relationships still have meaning. Your achievements and struggles and joys and sorrows remain important on a human scale. But they exist against a background of cosmic distance that puts them in context. that reminds you they're occurring on a small planet in a vast universe during a brief moment in cosmic history, while surrounded by structures and distances and timescales that dwarf anything humans can experience directly. Some people find this perspective disturbing. The scale feels overwhelming. The isolation feels lonely. The vastness makes existence seem meaningless, small, lost in an incomprehensibly large cosmos that doesn't care about human presence or survival. But this response, while understandable, misses something important. The universe's size doesn't diminish you. It's not a judgment. It's not a commentary on your worth. It's simply a fact about the structure of reality, a description of how space and matter and energy are arranged across distances that exceed human intuition. You can choose to respond to this fact differently. You can recognize that you exist in a cosmos capable of producing observers, that the universe organized itself over billions of years into structures complex enough to study it, that consciousness emerged from unconscious matter through processes we're still working to fully understand. You can acknowledge that being small doesn't mean being insignificant, that observing the universe from a tiny vantage point is still observing it. That understanding cosmic distance is itself a remarkable achievement for creatures who evolved to understand much smaller scales. The distances we've discussed, the scales we've explored, the barriers we've encountered, these aren't obstacles designed to frustrate you. They're simply the architecture of reality. The universe is structured this way. Space is large. Objects are separated. Light takes time to travel. Expansion creates horizons. These facts constrain what's possible, yes, but they also create the conditions under which complex structures can form, under which galaxies can exist without immediately colliding, under which stars can burn for billions of years, providing stable energy sources for potential life. If the universe was smaller, if distances were more human scale, if you could walk to nearby stars or drive to other galaxies, the cosmos would be fundamentally different. It would be denser, hotter, more chaotic. Stars would interact gravitationally more frequently. Collisions would be common. Stable planetary orbits would be rare. The conditions that allow for long-term stability, for the slow, patient process of stellar evolution and planetary formation and biological development, depend on the universe being mostly empty, on distances being vast, on structures being separated by gulfs that keep them isolated from disruptive interactions. The cosmic distance that makes the universe feel lonely is the same distance that makes it stable enough for observers to exist. The isolation that seems profound is the isolation that allows for the development of complex structures over billions of years without constant disruption. The barriers that prevent you from visiting distant galaxies are the same barriers that prevented those galaxies from disturbing your galaxy's development, that allowed the sun to form peacefully, that gave Earth time to cool and develop an atmosphere and eventually produce life. You exist because the universe is vast. You observe because structures had time and space to develop complexity. You understand cosmic distance because you're the product of a cosmos large enough and old enough and stable enough to create entities capable of comprehension. The scale isn't hostile, it's necessary, it's the framework within which your existence became possible. And within this framework, within this vast expanding cosmos, with its unreachable horizons and its distant galaxies and its immense voids, you remain capable of wonder. You can still look up at the night sky and see light from distant stars. You can still observe galaxies through telescopes and know that you're seeing structures millions or billions of light years away. You can still study the cosmic microwave background and recognize that you're observing light from the early universe. The distances don't prevent this. They enable it. They create a universe rich enough and complex enough and old enough to study. This is what cosmic distance ultimately means. Not that you're small, though you are. Not that you're isolated, though you are. Not that the universe is indifferent, though it is. But that you exist in a cosmos vast enough to contain structures at every scale, old enough to have developed complexity, transparent enough that light from distant regions can reach you, and organized in such a way that consciousness could emerge and turn its attention outward to observe and understand and contemplate the whole. The distance that breaks your brain, that exceeds your intuition, that makes numbers meaningless and comparisons fail, is the same distance that defines the structure of reality. It's not an obstacle to overcome, it's the canvas on which existence is painted. the framework within which stars and galaxies and planets and observers exist. Understanding it doesn't require conquering it or crossing it or making it smaller. It requires accepting it as it is and recognizing that your small presence within it, your brief moment of awareness in cosmic history, your capacity to observe and think and know, represents something remarkable in a universe that is mostly unconscious matter, separated by distances too vast to cross. Let's return to where we started, to the simple word that began this journey, and see how its meaning has changed now that we've traced its implications from human scales to cosmic horizons. Distance is the word we started with. You understood it then as something simple, something familiar, the gap between locations, the space you cross to arrive somewhere else. A measure of separation that effort and time could overcome. You understand it differently now. Distance, real cosmic distance, is not a gap to cross. It's a fundamental feature of how the universe is structured, how reality organizes itself across scales that begin at the familiar and extend into the incomprehensible. It starts with the distances you can walk, the spaces your body knows, the separations that feel manageable because you've experienced them. And then it expands. It grows through planetary distances that require machines to traverse, through interplanetary distances that demand spacecraft and months of travel, through interstellar distances that exceed human lifetimes even at impossible speeds. It continues growing through galactic distances that light takes thousands or tens of thousands of years to cross, through intergalactic distances measured in millions of light years, through cosmic distances so vast that light from the farthest objects has been travelling toward you for most of the universe's history. And finally it reaches the ultimate distances, the ones bounded by horizons, the ones that expansion makes unreachable, the ones that separate causally disconnected regions of reality from each other. At every step of this expansion, your intuition failed a little more. The numbers stopped making sense, the comparisons broke down, the timescales exceeded anything you could relate to lived experience. This failure wasn't a deficiency in your understanding, it was the inevitable result of trying to comprehend distances that operate on scales billions of times larger than anything human evolution prepared you to grasp. Your brain developed to navigate environments where the farthest visible object was miles away, where journeys took hours or days, where distance was something you could feel in your muscles and measure in footsteps. The cosmos doesn't operate at this scale. It never has. It never will. The distances between stars, between galaxies, between the structures that populate the universe, these distances are so enormous that they make human scales irrelevant. They create a universe where most of space is empty, where objects are isolated from each other by gulfs that light takes years or millennia or eons to cross, where the expansion of space itself creates barriers that nothing can overcome. And yet, within this vast cosmos on a planet 8,000 miles in diameter, orbiting an unremarkable star in an ordinary galaxy, consciousness emerged. You emerged. Entities capable of observing the universe, of collecting the light that arrives from distant structures, of processing that information and building an understanding of the whole. You cannot cross the distances. You cannot visit the far galaxies or step outside the observable universe or travel back in time to see the early cosmos directly. But you can observe, you can measure, you can study the light that completes its billion-year journey and arrives at your telescopes carrying information about the distant past. This ability to observe, to know about regions you cannot reach, represents a kind of bridge across cosmic distance. Not a physical bridge because the barriers remain absolute, but an informational bridge, a connection created by light, by the photons that cross even the largest voids to reach observers capable of detecting them. Distance isolates, yes, but observation connects. You are separated from distant galaxies by spaces you will never cross, but you are linked to them through the light they've sent, through the information that arrives despite the distances involved. You are small, unquestionably, undeniably small compared to galaxies and galaxy clusters and the observable universe itself. Your planet is a speck. Your existence is brief. Your physical extent is negligible by cosmic standards. But you are also the thing that knows, the thing that observes, the thing that has developed the capacity to understand that the universe is vast and old and mostly empty, that distances exceed intuition, that horizons exist beyond which nothing can be observed, that the cosmos extends far beyond what you can ever hope to fully explore. The universe produced you through billions of years of stellar nuclear synthesis and planetary formation and biological evolution. It organized itself through purely physical processes following physical laws into structures capable of comprehending it. This is what you are, a small localized region of organization and awareness embedded in a cosmos that is mostly unconscious matter spread across incomprehensible distances. You are what happens when the universe becomes aware of itself, when matter arranges into patterns complex enough to observe and think and understand. Distance shaped your existence. The vast spaces between stars gave your solar system time to form without disruption. The isolation of galaxies allowed the Milky Way to develop peacefully. The emptiness of cosmic voids provided stability for billions of years, while complexity slowly emerged on at least one planet and possibly others. The scale that feels overwhelming, the distances that break intuition, these are not obstacles to your existence. They are prerequisites. They create the conditions under which observers could develop. And now you exist in a universe where you can see structures billions of light years away, but cannot visit them, where you can observe the distant past, but cannot know the present state of far regions, where you can measure the expansion of space, but cannot prevent distant galaxies from receding beyond the horizon. You're confined to a small region of space and time, surrounded by distances you cannot cross, observing a universe that is mostly beyond reach. This is not a tragedy. It's simply the reality of existence in a cosmos structured by distance, shaped by expansion, bounded by horizons. You are here, now, in this brief moment of cosmic history when the observable universe is relatively large, when many galaxies remain visible, when the light from distant structures still arrives carrying information about the early universe. You can look outward and see not just space but time, not just galaxies but history, not just light, but the evidence of a cosmos that existed long before you and will continue long after. The word distance means something different to you now than it did before. It's not just separation, it's history, it's isolation, it's the framework that defines what's possible and what remains forever beyond reach. It's the measure of how reality is organized across scales that begin with the familiar and extend to the edge of observation. It's the space between stars, between galaxies, between causally disconnected regions of the universe. It's time measured in the journey of light. It's the barrier that expansion creates between what you can observe and what will remain unknown. You are small in a vast universe. You're brief in a cosmos billions of years old. You're isolated on a planet separated from other structures by distances that exceed your ability to cross them. And you are aware. You can observe, you can understand, at least partially, what these distances mean and how they shape the universe you inhabit. That awareness, that capacity to know, doesn't change the distances. The gaps remain vast, the barriers remain absolute, the universe remains overwhelmingly large and mostly empty. But awareness changes you. It gives you perspective. It shows you where you exist within the whole. It reminds you that being small doesn't mean being meaningless, that brief doesn't mean insignificant, that isolation doesn't mean disconnection. You are a small observer in an immense cosmos, looking outward across distances that break your brain, seeing light from galaxies billions of years old, knowing that most of the universe is beyond your reach, but not beyond your ability to study and comprehend and wonder at. The distance is vast. You are here. That is enough.